Alright, hey everybody, welcome back all. I hope you had a lovely break, a safe break. Hope you guys all found something to do stuck at home. But we are back, it's good to be back. I missed all of you guys. We are in the fourth quarter now, so if you didn't see my posting from April 8th, pretty much I said that homeworks are going to be counting for much more. It's just going to be weighted more, just purely due to the fact we're on an online platform, and so homeworks are pretty much the only way I can make sure you're actually watching the lessons and keeping on track with what we're doing. Alright, so it's going to be the same schedule. I'm going to be posting Monday, Wednesday, and Friday. You'll have 2 days to get your homework in. So if for some reason you can't hand in the homework in those 2 days because something came up, just let me know. Alright, but yeah, just make sure you get your homeworks in on time, or if there's an issue, send me a message. Alright, so welcome back again. What we're doing today is something called the WhatPower function. So before we get there, try to warm up. So as always, pause the video and take a minute or two and try these two problems. Oh, and the second problem, that is are very similar to the bonus from our last test, or our first test. So if you didn't check the answer key for that, you might struggle with that one, because it is a bonus conceptual-wise kind of question. Alright, so for this first one, this is a Regents problem. The answer is choice 2. So the function P of t models the population of a city in millions t years after 2010. As of today, consider the following two statements. The current population is 110 million. So t years after 2010, that means that was the initial population at t equals 0. So in 2010, the population was 110 million. So as of today, well, today I guess would be 2020. So if you want to find a population today, we will have to plug in t equals 10, which would obviously not still give us 110 million. So this statement is not supported by the model. Statement 2, the population increases continuously. So a continuous increase, we know we're going to use our PERT formula, right? Where E is Euler's number, around 2.718. So this is a continuous increase because it's of this form, PE to the RT. So our rate here is 0.03922, which is about 3.9%. So that is choice 2. Alright, for this one, we have something raised to some power is equal to 1. So when we have a number raised to another number, when is this going to equal 1? That's the big question. So essentially I'm making x squared plus 5x plus 5. I'm making all of that a, and I'm making this entire exponent, let's call that b. Alright, so if I have this situation where something's raised to some power, when does that equal 1? Well, that's going to equal 1 when a is equal to 1. Right? Because if we have 1 to any power b, that's going to equal 1, of course. Right? 1 to the any power is 1. And that's also going to equal 1 when, well, another exponent property we should know is a number raised to the 0 power is equal to 1. Right? So we can say when b is equal to 0. So when that exponent's 0, anything to the 0 power is also equal to 1. So let's take a look at these two scenarios and see what that looks like. So here we are. Boop, boop. Need a little more style. Bam. Alright. So when a is equal to 1, what I'm going to do is I'm going to set my a which is the base, x squared plus 5x plus 1, or sorry, x squared plus 5x plus 5 equal to 1, and solving for that, we get solutions of -4 and -1. Right, when b is equal to 0, we're going to set our exponent, x squared minus 10x plus 21 equal to 0, and then we get those two solutions of 7 and 3. And I'm hoping most of you are able to think of these two scenarios, right, and evaluate at least these 4 values of x. But there is another case when a number raised to another number is equal to 1. And that is when, well, I'll give you the first part, when a is -1. If a is -1, what kind of value does b have to be? And that is when a is -1 and b is equal to a even number. Right? Because we know if we have -1 raised to the second, -1 in parentheses now, right? That's going to equal 1. Or -1 raised to the 4th, or to the 6th, or to the 8th, or to the 10th, etc. Right, so we can say in general raised to the 2n power, where n is a whole number, right, because 2 times any whole number will be even, or in other words, b has to be even number. So let's see what happens in this scenario. So we're going to have x squared plus 5x plus 5 equal to -1. Solving this, x squared plus 5x plus 6 is equal to 0. X plus 3 and x plus 2. When we factor, solutions of x equals -3 and x equals -2. So these values of x are going to give us a base of -1, right? We solved for this part. So right now we have -1 raised to some power. So that power has to be even. So we have to check, do these solutions we found give us a even exponent? So our exponent was x squared minus 10x plus 21. So x squared minus 10x plus 21, is that going to give us an even exponent? And this is 9 plus 30 plus 21, which is 60. So when x is -3, what happens is we get -1 to the 60th power, right, which is equal to 1. That checks out. This is a valid solution. Let's check what happens when we plug in a -2. We would get -2 squared minus 10 times -2 plus 21. Right, and that's going to be 4 plus 20 plus 21, which is 45. So when x is -2, yes, the base is -1, but we're going to be raising it to an odd exponent, 45, so that's going to give us -1. So we need to reject this answer. And so the sum of all the solutions is going to be -4 plus -1 plus 7 plus 3 plus -3, and that is equal to 2. Alright, so that was some good review. On to today's lesson, the WhatPower function. So in class, I probably just let you talk with a neighbor and try to figure this out based on the first 2 completed problems. But I see WhatPower and then a little subscript 2 with an 8 in parentheses, and that's equal to 3. So what the heck is going on here? So the name WhatPower, maybe that will give you a hint. So I know like 2 to the 3rd power is equal to 8. Let's see if that's what's happening on the second example. Yeah, is 3 squared 9? Yes, it is. So what this function is actually doing is it's saying what power of 2 is equal to 8? And the answer is 3. Right? This is saying what power of 3 is equal to 9? And the answer is equal to 2. In other words, this can become 2 to the 3rd power is equal to 8. This is becoming 3 to the what power? 3 to the 2nd power is equal to 9. So this next example says, what power of 6 is 36? So 6 to the power of 2 is 36. 6 squared is 36. This is saying 2 to the what power is 32. So 2 to the what power is 32, right? I can call this an x here for the what power. All right, that'll be the x here. So 2 to the 5th power is 32, so that is 5. 10 to the what power is 1,000. 10 cubed is 1,000, right? 10 squared is 100, and another 10 is 1,000. 10 raised to the what power is 1,000,000. So if you count the zeros, we got 1, 2, 3, 4, 5, 6. So 10 to the 6 is equal to 1,000,000, right? We could write it like this. 1, 2, 3. 100 to the what power is 1,000,000. We have 2 zeros, so let's count sets of 2 zeros. 1, 2, 3. So 100 cubed is 1,000,000. All right, 4 squared is 16, and 4 cubed is 64. What power of 4 is 64? The third power of 4 is 64. All right, so the examples on the right are a little trickier. Same idea though. So take a minute or two and try these. All right, pause the video. Go, 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 go. All right, let's check. Hopefully you are getting 6, half, half, 3, 0, -1, -2, -1/2. So I will go over some of these. Example 10. 9 to the what power is 3? I'll use an x here, right? 9 to the what power is 3. Well, we know the square root of 9 is 3, or 9 to the half is 3. Right? If you want to use method of common bases, you can also do that. You can say 3 to the 2x is equal to 3 to the first. Right? 2x is equal to 1. The bases are the same. We can set the exponents equal to each other. X is a half. Right? Same thing here. 5 to the half is the square root of 5. A half cubed is 8. Right? 42 to the what power is 1? Well, we know any number raised to the 0 power is equal to 1. All right, 100 raised to the what power is 0.01. So 0.01 is 1 over 100, by the way. So that's 100 to the -1st. All right, and same idea, I'll do over the last two. 2 to the what power, I'm going to call it x for the power. All right, so let's pretend we don't know the answer. 2 to the what power, let's call that x, is equal to 1/4. So if I'm doing the method of common bases, well, I know 1/4 is equal to 2 to the -2nd power, right? It's 1 over 2 squared, which is 2 to the -2nd, and so x is -2. Right, and for this last one, we have 1/4 raised to the what power is equal to 2. So we just said 1/4 was 2 to the -2. So I can make that 2 to the -2 to the x is equal to 2. 2 to the -2x, right? Power to a power. We can multiply the exponents. Equals 2 to the first. -2x is equal to 1. X is -1/2. So let's just check our answer. Is 1/4 to the -1/2 power. That's the what power we were looking for. Does that equal 2? Negative exponents tells us to take the reciprocal and raise it to a positive exponent. And yes, the square root of 4 is 2. So there we go. And spoilers, but I'm sorry guys, the WhatPower function is not a real thing. It's just something I made up, but it is how I want you to think about what we're actually doing. And what we're actually doing is what we call logarithms, right? The WhatPower function is really logarithms. So you probably saw it. I probably should have made the font even smaller. But this is the real topic of today, logarithms. Right? And logs, they're always pretty confusing for a lot of people, which is why I introduced it as the WhatPower function. But pretty much what we should be able to do with logarithms right now is to go from logarithmic form to exponential form. All right, so logarithmic form. To exponential form. All right. So when I said the WhatPower function was a logarithm, well, it means we could have said log base 4 of 64 is equal to 3. All right, WhatPower is log. So if I have this, that's logarithmic form. All right, it's saying pretty much WhatPower of 4 is 64. So we know 4 cubed is 64. Well, in exponential form, right, we can go back and forth either way, but this is saying 4 to the third power is equal to 64. All right, let's do another example. In log form, if I have log base, 2 of 8, what does that equal? That's equal to 3. Right? I want you to think of this as WhatPower of 2 is 8, and the answer is 3, because 2 to the third power is 8. In exponential form, this would be 2 to the third power is equal to 8. All right? So the definition of a log is just going to be the general form of these examples. So our formal definition is going to be log base b of a equal to c. And what that gives us is, well, again, this is saying b to the WhatPower is equal to a. So to convert, it might be helpful to know that the base here, right, that's going to be the base of the exponent. Right? This is the WhatPower function, so what it's equal to, that is the power, that is the exponent. So this is equal to c, so our exponent is c. So this b to the c power is equal to a. So there are names for all of these things. Both of these equations describe the same relationship between a, b, and c. All right, and over here in log form, we call b the base. It's also the base in the exponential form. All right, the c here, that is our exponent. C is the exponent. And that a is what we call the argument. All right. So let's graph this function y equals log base 2 of x on the axis below by making a table and including at least 3 points. All right. So what I'm going to do first is I'm going to change this to, actually, let's just try to use the equation as it's given. So x comma y. So what you might try to do is just plug in a random value for x like we would normally do. So if I plugged in the 5 for x, this is saying 2 to the WhatPower is equal to 5. And I don't know 2 to the WhatPower is 5. 2 to the WhatPower is 5. I have no idea. It's going to be in between 2 and 3, right? Because 2 squared is 4 and 2 cubed is 8. So I don't know 2 to the what is 5. So we might have to like cherry pick our values for x. For example, I could do 4 because I know 2 squared is 4. So that'll be 4 comma 2. But that's probably pretty complicated to think about like that. So what I'm going to do is I'm going to change this to exponential form, and that's going to be a lot easier to work with. So our base here is 2, right? This is the WhatPower function. This was equal to y, so our power here is y. And so this is saying 2 to the y is equal to x. So normally in a function, we plug in for x, right, to get the y value. But the way this is written, it makes a lot more sense to plug in for y and figure out the x value. So for example, here, when y is 2, our x value is going to be 4. So let's see, when y is 1, 2 to the first, that's going to be 2. When y is 0, 2 to the 0, that's 1. When y is negative 1, 2 to the negative first is a half. Right? I'm going to get a couple more values. Let's plug in a negative 2 for y. When y is negative 2, 2 to the negative second is a quarter. 2 to the negative third is an eighth. Right? 2 to the positive 3, that's 8. So let's plot these points and see what this function looks like. All right, we got 1, 0, 2, 1, 4, 2, 8, 3. What is it? A half, negative 1. So right there. A quarter, negative 2. So right there. An eighth, negative 3. Can you guys see what's going to happen? We're going to have a 16th, negative 4, a 32nd, negative 5, a 64th, negative 6. I forgot what number we're up to. A 64th, a 128th, 256, 512. Right? So, are we ever going to go past this y-axis? Well, the answer is no. Right? Let's just plug in one more negative value. Let's say I had like negative 100. Well, what value of x is going to give us a y value of negative 100? Well, x then is going to equal 2 to the negative 100th power, or 1 over 2 to the 100th. And that's still a positive value. It's just a very, 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 very small positive value. So what's happening is we're going to have a vertical asymptote here. Right? We're never going to cross this y-axis. And so when I draw my graph, it should look something like this. All right? And your graph should absolutely not pass the y-axis. Because what is happening is we get closer and closer and closer to the y-axis. But our function will actually never reach it. It's never going to equal 0, right? We're always going to have 1 over 2 to the some power. And so it's never going to be negative. It's never going to equal 0. We have a vertical asymptote. As our y-axis. And the equation of that, of course, is x equals 0. Right, so here is our graph of log base 2 of x, or y equals log base 2 of x. And some good things we should talk about. Let's talk about domain and range. The domain here, well, we have all the x values greater than 0. So our domain is x is greater than 0, or in interval notation, 0 to infinity. Right, our range, this is going to keep going down. This is going to keep increasing also, by the way. Right? There's no limit to what the y value is going to be. I can make it 4, 5, 6, right, a million. It's just going to grow really, really slowly, but it's always going to keep increasing. So our range goes from negative infinity to infinity, or we can say y is an element of the real numbers. All right. And on the same axes, I want you to graph y equals 2 to the x. So this should be a lot more familiar, hopefully. I'll put 0 in the middle. So y equals 2 to the x. So y equals 2 to the 0 here, and that's 1. When x is 1, 2 to the first is 2. When x is 2, 2 squared is 4. That's going to be 3, 8, negative 1, a half, negative 2, a quarter, negative 3, and eighth. And I'm hoping you see some similarities between this table and this table. Right? If you don't see the similarities, maybe you'll see it when we graph it. So we got 0, 1, 1, 2, 2, 4, 3, 8, 4, 16, etc. Negative 1, a half, negative 2, a quarter, negative 3, an eighth, a 16th, a 32nd. Right? Same idea is happening here. Right? Except it's going to be a horizontal asymptote in this case. I'm not going to draw that in, but do we see what is happening with our graphs? Do we see what is happening with our tables? All right, what can we say about y equals log base 2 of x and y equals 2 to x? These functions are, right, hopefully you are thinking, they are inverses of one another. They are inverse functions. All right, logarithmic functions and exponential functions are inverse functions of each other. All right, so in the table you can see 8, 3, 4, 2. Those become 3, 8, 2, 4, right? The x and y values are flipping. Graphically, bam, it's a reflection over the line y equals x. Our vertical asymptote became a horizontal asymptote, right? X equals 0 became y equals 0. 4, 2 became 2, 4. Right? Inverse functions. Our domain and range, they also flipped, right? The domain of this guy is negative infinity to infinity. Right? The range is y is greater than 0. Right? Domain and range flipped. Everything flipped. These are inverse functions of one another. So let's add that over here. Right? Logarithmic functions and exponential functions are inverses, are inverse functions. Exclamation mark. Cool? All right. So, well, let me actually show you that algebraically real quick. Right, we said y equals log base 2 of x can be written as 2 to the y. Right, so if I want to find the inverse, well, do you guys remember how we find inverse? Step 1 was to flip x and y. Right, so that'll be 2 to the x is equal to y, and then solve for y. It's already solved for. So the inverse function, replace y with the inverse function, is 2 to the x. And that is exactly what that is, right? They're inverse functions. All right. So what values of b in that expression might be problematic? What can't we have for a base? So let's write this in exponential form. This is going to be b to the y is equal to x. So what kind of values can't we have for b? So if I want to avoid problems, I'm not going to make b equal to 0. I'm going to first of all say b can't equal 0. Because if b were 0, I would have 0 to the y is equal to x. And that's always going to equal 0. Right? So that's not going to be an interesting thing. I mean, technically b could be 0, but it's going to be problematic. Right? So we're not going to allow a base of 0 for our log function. All right? For the same reason, we're not going to have a base of 1. Because if we have 1 to the y power is equal to x, well, x is always just going to equal 1. Right? It's not interesting to consider this case where b is equal to 1. So we're also going to say b can't equal 1. And so those are always values we check. We can check positive numbers, but we should also check negative values. And for the same reason, because this is connected with the exponential function, y equals b to the x, right? These are inverse functions of each other. Because these are inverse functions, and we know for exponential functions the b value can't be negative, we're not going to allow negative b values either for our log functions. So we're also going to say b has to be greater than 0. All right? We could say greater than or equal to 0, but then b can't equal 0, so I can actually just combine it with this statement. And this is saying b can't be negative, b has to be also greater than 0, and b also can't equal 1. All right? And again, the reason b can't be negative in an exponential function is because, well, we see the problem. If b is negative 2, for example, right, it's not a continuous function. It's really not something we want to consider. For example, when x is 1, y is going to be, we're going to have 1 comma negative 2. When x is positive 2, we're going to have 2 comma 4. When x is 3, we're going to have 3 comma negative 8, which is down there, then 4 comma 16. Right, and then in between, we're going to have like all sorts of crazy values. It's going to be undefined or imaginary, a whole bunch of places. It's just, technically it could be negative, but it's not something we want to consider. So for us, we are going to define the log function to have b greater than 0. Right, the base is always defined to be positive in the exponential function. The base must be positive in an exponential function. And so because this is the inverse of exponential function, we're also going to make the base positive in log functions. All right? And b cannot equal 1. All right, let's just take a look at this invalid thing. But let's say log base 1 of 3 is equal to x. Right, this would be saying 1 to the what power is equal to 3. Well, I can't raise 1 to any power and get 3, right? Same thing if this was log base 0, right? 0 to whatever power x is not going to equal 3. So we're also going to say b cannot equal 1 over here. Right, and lastly, I know this is only asking for values of b. But let's take a look at this x value also. Right, so this x value, that's our inputs, that's going to be our domain. But we also know x has to be greater than 0. Right, our domain. This is only valid for x values greater than 0. So again, the reason is if we define b as being positive, right, b to the y power equals to x. If b is a positive number, can this ever equal a negative value? Answer is no, right? You can't raise a positive number to some exponent and get a negative value. So our domain also has to be x is greater than 0. All right. So if we look at number 5 here, what is the domain of y equals log base b of x given our restrictions for b? That's actually what I wanted to talk about down here. I jumped the gun, sorry. But our domain has to be x is greater than 0. Because, again, this means b to the y is equal to x, right? And because a positive number, b, because b is greater than 0, a positive number raised to any power is positive. Right? Meaning that b to the y also has to be greater than 0. So it follows that if b to the y is greater than 0, well, that is also x. So our domain has to be x is greater than 0. Right? And we see that here when we graphed it. When we graphed our log function, right, our domain was x is greater than 0. All right? So that is your intro to log functions. Next homework assignment is going to be due on Wednesday at, I don't know if I made it 9 or 10 o'clock, but 9 or 10 o'clock, just get it done before, don't do it the morning of. But that's that. Again, stay safe. Looks like things are starting to get better, so probably won't see you this year, but stay safe again, and miss you guys. See you guys later.